Welcome. Today we talk about algebra. I want to focus on two things: solving the cubic and solving the Rubik puzzles. So they seem to be completely unrelated things, but they are all essentially the same thing. It's essentially all group theory. Also the symmetries, if you look at symmetries of geometric objects, then we have to deal with this type of mathematical object. You will see that there will be one object which actually appears in all three cases. So there is one Rubik type puzzle which we are going to look at more in detail. It's my favorite, and it is a puzzle. It is also a symmetry group, and it's also a Galois group, a symmetry of solutions to equations. Very exciting. And I want to start with part A, solving equations. So this started already with the Babylonians. They have solved linear equations, actually already systems of linear equations 4,000 years ago. And a really exciting moment is then around 830, with Al-Jabiri, who has found the solution of the quadratic equation. So here I have Al-Jabiri, and this house of Baghdad. It also is featured in a recent movie, the physician, and we will look maybe a little bit more into that movie. But it was an exciting time. But the algebra as we know it with variables came much later. So this is François Vieta, who was first really dealing with variables. So Al-Jabiri did not write variables like we do in school. Al-Jabiri found the solution of the quadratic equation, and then there was a race going on how to find solutions of more complicated equations like the cubic, the quartic or quintic, etc. We have formulas for the quadratic equation, and until 1545 there was a complicated kind of also battle between Tartaglia and Cardano and Ferrari. They were all kind of competing with finding solutions of the cubic, and but in 1545 one really had the solution to the cubic equation, and then came the quartic equation with Ferrari around the same time. So first of all, about the quadratic equation, we'll talk a little bit more about this, look at examples. How did was this formula derived? It's always a reduction step, so you see, maybe you can see it on the board, one always first depresses the equation. So one gets rid of not of the highest power, but the second highest power, and then it's easier. So for the quadratic equation, if you get rid of the middle part of the linear part, then you have only ax squared plus b is equal to 0, and then you can solve it with taking square root. And the same thing works also with the cubic. You just first remove that translate, so that you actually have a depressed version, and then the depressed version is, with a clever variable substitution, can be reduced to a quadratic equation. Then you have a quadratic equation for a u cubed, so you have a cube root also appearing there. The quartic equation is similar. You just first depress it. The quartic equation, you depress it, and so this is kind of what we do here. This is the Cardano Tartaglia formula. So first of all, depress it, x minus a third, and then you get a depressed version, and the depressed version is done with a clever substitution. It's just quite simple to check that, and then you get an equation which is a quadratic equation for u cubed, and then you can solve that. It's very simple if you know it. But we will see also these puzzles here. They are very, very simple once you know how to do them. But if you have never seen them, finding the solution can take you a long time. And I spent for the Rubik cube as a high school student 3 weeks to get this done. Of course, not looking it up, that's cheating. But you have to kind of find out what do things do, and what happens if you actually move things. What happens with the individual pieces, and also that finding the solution here of the cubic equation required a lot of examples trying out what happens when I do this, what happens when I do that. This is not so much appreciated anymore because you have the internet and you can look up things, but if you have not seen it, finding that cubic equation is hard. Similar than all these puzzles are hard if you have never done that. It's maybe except with the exception of this one, which is kind of my favorite here, which is which we are going to look at, which you cannot do otherwise than solving right away. And then the quartic equation, that was Ferrari. We don't have a picture of Ferrari, so I put a picture of a car. And so again, you do the same thing. You first subtract minus b fourth to get the depressed version, and then comes a clever new idea. So you write it as a product of two quadratic equations, and then you have a system of equations for variables which you can solve using the cubic. So that's what Ferrari did. He reduced it to the cubic. So quite ingenious. And then the question is, what happens afterwards? What happens when you have the quintic? How do you solve the quintic? And this also, that took actually, you see, the time. It took 250 years it took to find that. And actually there were three who kind of should be credited with that. Ruffini is kind of my favorite because, first of all, he's kind of usually not mentioned, but he was way before. He was 1799. He already saw that one cannot do it. It's not maybe written down in the most clear way, but the other guys also, maybe Abel was writing it down clearly. Galois was writing it down just before he was killed, right in the night, and I have no time, but almost not writing really the details down. But this is an equation, an example of a quintic equation which you cannot solve using formulas, using roots. And that's related also to a ruler and compass constructions, right? When you want to construct, for example, an angled trisector, you want to do that. That's also related to that. That you can prove that using the same mathematics, that this is not possible using ruler and compass. It's quite a nice thing, and that the Galois, so that leads to a whole new world. Hermann Weyl once wrote, "This letter, if judged by the novelty and profundity of ideas it contains, is perhaps the most substantial piece of writing in the whole literature of mankind." It's an amazing idea, and he wrote that just before he was killed in a duel, probably an affair, love affair. This was then the end of Galois. The relation between this story and this story is really kind of group theory. So when you look at all the possible roots and you look at all the permutations of these roots, there are 5 roots. Then you have what one calls a group. We will talk about this a little bit. This is called a permutation group. And for 3 or 4, it is a solvable group. For 5, it's no more solvable. Related to the fact that we cannot solve the quintic anymore. The symmetries, we will talk about this in class. Also, there's a reflection symmetry which you can apply. And this reflection symmetry, there's first of all the identity, which when you do nothing, and then there's when you apply the symmetry here, which is reflection. And so when you do the reflection twice, you get again to 1. So this is what one calls a group. This is S2, a symmetric group of its 2 elements. Now for a triangle, and that's what we will talk about then also, we'll actually write down this multiplication table. What happens when you take the identity, when you take a 120-degree rotation and you apply a 240 degree rotation, what happens? Of course, then you are back to the identity. So when you take 120 times 200, you are back to the identity. So we will fill out this what one calls multiplication table, and also for a rectangle and for the square if you have time. But the most exciting really place where groups appear is when you look at puzzles. The first one which actually appeared is this 2 times 2 times 2 puzzle. Where is it? I had one, I'm sure I had one. Yeah, this is the one which actually appeared even before Rubik. So it's quite a intriguing puzzle. If you have never done that, you will, and you don't look up how to actually do that, you will spend days. I myself used 3 weeks to actually find the solution of the Rubik, and it was quite awkward, and I needed quite a bit of time. So I had kind of moves like this. I just, you know, built moves which do something and which I know what happens, and then I can combine them. So it is a little bit of a, you know, try and error. You have to kind of play around with this a lot, and really kind of almost dream about it in the night in order to get the solution done. So that was historically the first, and then came the famous Rubik thing. It really exploded in the 81. That's when I really also got hooked in high school, and so this is the famous Rubik cube. But it's also a group, because when you are doing something, you apply some operation like a symmetry operation or a flip of the roots there, and when you do another move, you apply another. So you can combine them, right? You can take 2 elements and combine them to get a new one. But these groups are huge. So this is a fantastically large group. Essentially, it is so you have 8 corners, so it's 8 factorial, 12 side, 12 factorial, and then you can flip each of them. So this is 3 to the 8, and then 2 to the 12, and then you divide the whole thing by 12. So it's absolutely fantastic for the Rubik, right? So for the Rubik, how many possibilities do you have? So you have 8. So what do you have? 8 factorial times 12 factorial times 3 to the, so each of these things you can turn by 3. So 3 to the 8, 3 to the 8, and then 2 to the 12. But not everything is possible. So not every kind of, you cannot turn 1 alone here. So the whole thing is then just divided by 12. So these are the number of elements in this group, which is huge. Now other groups are smaller. I like this. We might talk about this. This is the floppy, which appeared pretty late. I think it's only about 2001. Anyway, I only got it here. I had a trunk full of such puzzles in high school, but they all left in this state in Switzerland. But I bought new ones here, and this one I only got maybe 10 years ago. So this is actually quite an interesting one also, because there's some geometry going on. So you actually have can do things like this. So I can turn it, and then I can turn actually one of these pieces. Let me just see whether this works. Actually, this was possible. How do I do that? I can do that like that, and then I can turn. No, in this case, oh no, I can't do it. I can turn one, and then I can turn back. So you see, kind of, I've actually managed to turn one. Physicists call this a quark. This is a quark, which is in this case not possible. So there are 2 quarks. Quarks and antiquarks exist together. This forms a meson, and then you have a baryon, which is a baryon which has three made of 3 quarks. This is also possible. So, but in this case, it's kind of intriguing that you also can do things which you cannot do in the Rubik cube, right? You can actually do things in space. When I got this one here, I was actually thought it's trivial. It's called the pyramids because it's pyramid, right? Actually, this one here I got first. This one I had already in high school. This I had myself. This is actually very similar to the Rubik. You cannot change the geometry when you are moving here, and you can also move the corners, right? So this is actually quite similar than the Rubik cube. So this one is remarkable because you can change the geometry, right? When you actually do that here, you can get to a bow tie thing, or then you can turn it again, and then you can get to a spaceship. Right? So you can get different geometries, and now you can turn things around like that. So they are very, very geometrically just intriguing, right? So that you can do things like that, which you actually cannot do with the Rubik cube. Especially this puzzle here is my favorite, because you cannot you cannot actually do it wrong, and it's related to solving the cubic, because what you do is if you fix one of the corners here, and you move this or this. Now if you turn it twice, then you don't do actually anything. So the only thing which you can actually do is just turn, 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 and it's already solved. So but what happens actually when you do it is 1, 2, 3, 4, 5, 6. So there are actually 6 possibilities. And these 6 possibilities are actually all these 6 possibilities we have here for the symmetry group of the triangle, and it's also the Galois group of a general cubic equation. So this is S3. So this is what we call S3. So all the permutations with 3 elements, and it's already not commutative. So when you do AB, it's not equal to BA. Right? So we will do that in class, but it's different. If you take A and B, that's not the same thing when you take B times A. It's just a different thing. And that makes these puzzles also interesting, right? If you take this is the 4 times 4 times 4 cube, which I also had in high school. So when you take the first one and then the second one, that's a different thing. Then when you take the second one and then you take the first one. So it's amazing how fast people can do these puzzles. I was exposed to this 15 puzzle as a small kid already, much earlier than the Rubik cube. It's a very interesting puzzle, and interestingly, one doesn't know the shortest path. You know, how many moves do you know? Have to use minimally to do that. For the cube, one knows it. So the God number is 20. This is something which has been known, computer assisted. For this one, of course, you can do it in in 3. This one here is actually an interesting case. If you don't allow to turn things in space here, then you have 192 possibilities, and then I think the God number is 6. While you can just compute that out, because it's 192 is a very few cases. You can just look what is the largest distance you can get in all the possible paths. And so the God number is actually always kind of an interesting thing in that. So that's the Rubik cube. I mentioned this is 74. It kind of was invented by Rubik, and then it kind of in 81 it really exploded into an international thing, and people are doing things every year. They are producing.
19-year-old in Australia.
So we will talk about this floppy a little bit. It's a very beautiful case. It's really a manageable case also. The floppy is something when you take the floppy and you just scramble it arbitrarily, and then you want to do it. So what you do is you first just fix. So what you first want to do is just fix two sides. So how do I do that? So I have to switch that. So now I have this fixed. Once you have that fixed, that's actually exactly the same idea which you have when you go solving equations. You kind of reduce it to a case with less symmetry, which is a smaller case, and then now you can just, whatever you do, you will solve it. So there's no way you can get wrong. So it will be solved eventually when everything is right, and really that's what happens. So so these are puzzles which are quite easy to learn, but already this one here, 2 times 2 times 2, is much harder. So for this one, and so I think that's kind of what we have. Is there also people have done 3-dimensional cubes. You can actually do them with a computer, and that's it. And we'll talk more about this in class. See you there.